So now we're in chapter 3, polynomial and rational functions, and our first section is section 3.1, which is quadratic functions and models. So quadratic functions are functions that are polynomial but have a highest degree of 2. So they're kind of special because we do see them a lot. So if you have a function in this form, a, b, and c are constant, so they're just some sort of real number. A is not 0, which would of course get rid of the whole x squared part. Then you have a quadratic function. So a fact here, and there's kind of some pieces to it, is that f of x equaling ax squared plus bx plus c, if you have something in that form, it can always be written in this form. So it basically just requires some rewriting of it. You're doing some math there to kind of move things around, and you can write it in that form. If you have a quadratic that is written in that form, then what follows from that is that h and that k that you see there are the vertex. So the vertex is h comma k. As you know, parabolas look like this, and so they have this symmetry depending on where they are sitting on the Cartesian plane. So depending on where they sit, there is always a line of symmetry, which is coming from the h part of the vertex, the x part of the vertex. And you should also think about the fact that depending on whether a is positive or negative, you could have a parabola that opens up like a cup or down like a frown. So if that first constant is positive, you have something like this, and then you've got a minimum down here. If your a is negative, then your parabola is like this, and it has a maximum up there at the top. Okay. If you think about it, no matter how you slice it, no matter how you write it, if x is 0, then you're just left with c, which means you have a y-intercept at the point 0c, 0c. And if you were to take that function and set it equal to 0, so here you're making f of x equals 0, which is the same as making y 0, then you're going to be able to find your x-intercepts, the places on the x-axis where the parabola crosses it. And so that's like a whole lot about parabolas, and we're going to take a look at them and see what we can do to get kind of a general idea and a more specific understanding. So now we have a parabola. We have a quadratic function, so the way this would look if it was graphed is a parabola. We're asked to sketch a graph of it. So that typically means you want to be as precise as possible with the understanding that you're not going to put every single point on there. There's an infinite number of them, but some of the most important points, and then you're going to connect them, understanding that you already know the shape of a quadratic. So the best thing to do would be to write this in that form that we've already talked about, which is the f of x equals a x minus h squared plus k. So ideally, if we can rewrite this function, f of x equaling 2x squared plus 4x plus 3, if we could rewrite that in that form that I have down there at the bottom, we would immediately know the vertex. We would immediately know the line of symmetry. Now you might already be able to see that we can figure out the y-intercept pretty quick. If we put in 0, we can put it into this version. We don't need to rewrite it. You can see pretty quickly that you're going to have 2 times 0 plus 4 times 0 plus 3, which is going to give you 3. So pretty quickly you can see that you have a y-intercept of 0, 3. And that can go right onto your, your y-axis there. And now we have a point on our parabola. So in terms of how to rewrite this, let's go back up to the top here. The thing that you want to do is you want to separate your variable terms with your constant term. So basically I'm going to do this. And then I'm going to add or subtract something that completes a square. So the big thing here is we want to complete a square because we want to be able to write the x portion as a perfect square. Something times itself, as you can see. There's the little square there. Now that's easier or harder depending on your A. Notice that our A is 2. If A is 1, this is easier. Because A is 2, we actually have 2 steps we need to do. If A is not 1, excuse me, you need to pull out your A, you need to factor it from your first 2 terms. So I'm going to factor out my 2. I'm going to add a space. I'm going to subtract a space, and then I'm going to add my 3. So I have a plus blank and a minus blank, and I'm going to put the same number in each of those if my A is 1. If my A is not 1, it's going to be equivalent, and I'll show you why. So now I'm going to, let's see, what do I want to do? Okay, so the idea here is I want to add a value to this blank space that's going to complete that square, x squared plus 2x plus. Now we might remember from other stuff we've done, the way to find the value that we're going to put right there is to take half of that constant next to the x term. So we want to take half of 2, which is 1, and then we want to square it, which is 1. So the value we want here is a 1. That will complete that square so that we can rewrite it as something squared. Now, here is the kicker. If I add a 1 here, the whole idea behind adding something and subtracting something is I want to add or subtract something so that what I've really done is add 0. That's the idea behind completing the square, is adding 0. I want you to notice if I multiply out this 2 by the 3 terms that I currently have in my trinomial, I'm going to have 2x squared. I'm going to have plus 4x, yeah? And then I'm going to have plus 2. So notice I'm adding 2 because I'm adding 1 inside the parentheses, but if you multiply it back out, you're going to have a plus 2. So the opposite of adding 2 is actually subtracting 2. And that's why those numbers aren't the same, because A is not 1 in this case. If A were 1, we'd add and subtract the same thing, but it's not. But I want you to see that really we are adding and subtracting the same thing if you were to multiply out, distribute that 2. So now what we can do is just rewrite. And we have f of x equals 2. And then the whole idea there is that we've now just created a perfect square. Remember that the value that goes in the perfect square, the number, because it's going to have an x here, is just half of that middle term. So the middle term is positive 2, half of that is a positive 1. So it looks like that. Then we have a minus 2 plus 3, and we just combine those and we get plus 1. So this is the big idea here. We now have it in the form that we want it to be in. If you want, I can even write it in one other way, just so that you can see that when we look at this thing that we have here at the bottom, it's a minus h plus k. So the value in the middle with the x is actually the opposite of what you see. So in order to make x minus h, we have to do x minus -1. So that gives us a -1 for h and a 1 for k. So our vertex is -1, 1. It also tells us that the line of symmetry for this quadratic is x equals, and then it's just the x value of the vertex, -1. So it tells us the line of symmetry is important because it means you actually only have to do like half the values because you have that line of symmetry, and you know you have to be on either side of it. So you don't have to do the line of symmetry, but I'm just going to show you. Here's the line of symmetry at x equals -1. And then let me put the red back. So now I'm going to put on some points. So I know my vertex is -1, 1. So -1, 1 right here. There we go. And then really the big thing is just, we know that we have to be symmetric on either side of my line of symmetry. So I have the point 0, 3. I have to have the symmetric point too. So I have to have that point. And really, that's all we need. Now we know the shape of it, and so we can just go ahead and combine, our points, make it look like a parabola. We don't want to make the sharp lines, because that's not what it is. It's a parabola, and it's smooth. So we want to make sure we do that. And there's our parabola. Now what I want you to notice is, in this example, I haven't shown x-intercepts. I didn't do x-intercepts. Notice it doesn't have x-intercepts. And you could use the discriminant if you wanted to. You could pretty easily find from the discriminant, remember the discriminant is just b squared minus 4ac. So you can see pretty easily that you have 16 minus, looks like a 24, and that's going to be a -8. So the fact that this discriminant is less than 0 is telling us that we have no real solutions to setting that function equal to 0. And so it tells us that we don't have any x-intercepts because we don't have any places that are some x values that are real that give us a solution when you set it equal to 0. So this is telling us no x-intercepts. So using the discriminant to tell me that means I don't have any x-intercepts, I can see them. This function is above the x-axis, so pretty easy to see graphically. Okay, so now we have another one. Now, as we continue with these, you are very welcome to go ahead and do any of it that you can and then come back and watch the video. That would be great. Our y-intercept actually happens to be the same. You can see pretty quickly if we put 0 in for x, we're going to get 3. So we're at 0, 3, but don't get excited. We know that these two functions are definitely different. Do notice that in this case, a is -1. So that's good in some ways. Because it means completing the square is a little bit easier. Do notice that with a being -1, what we've already talked about is when a is negative, your parabola is going to go down like a frown. And so it's going to have a maximum and then it's going to come down. So that is a big difference between the last one and this one. So do note that. But otherwise, we kind of start just the same way here. We do the same type of thing. I'm going to pull out the negative. There's no value, that's not 1 there, that's just a -1. So I'm just going to pull out a negative. It's going to change the signs of the first 2 values. And again, my job here is to complete the square. So I'm going to be, taking these numbers and making it so that the whole idea here is I'm going to be adding 0. I'm going to add and subtract the same amount so that I've really added nothing. And the whole point of that is that that allows me to just rewrite it without changing this function. I'm definitely not trying to change it. So, okay, well, this one's very similar to the last one in that we have the same value that we need here, because half of 2 is 1, squared is 1. But notice what we've really done there is we have minus x squared minus 2x minus 1. So what I've really done by putting that 1 there is subtracted 1, and so I actually need to add 1 here. Because if I were to now multiply this out and combine like terms, I come back to my original. That's the whole point. So now we can rewrite. We have a negative, we have x plus 1 squared. We already knew that just because it's the same as the last one. And now we're adding 1 and 3 to get 4. So very similarly, we have the thinking about it if you want as x minus a -1. We have a -1 comma 4. And that gives us that same line of symmetry, x equals -1. Okay. But let's put some points on here. So we have -1, 4. And then we have our line of symmetry. So obviously some differences here. Now we should be seeing them. So line of symmetry, all the points need to be symmetrical on either side of that. So we can go ahead and put on this value here. And because that has to be symmetric over that line. And then notice this one does say x-intercept. So it's a good sign that there's some sort of real number value that might be helpful to us. So to find x-intercepts of any function, you set it equal to 0. If you're not a big fan of that negative x squared, you can multiply through both sides by a -1. And that's going to give you this, which is equivalent to what we just had in terms of the solutions when it's equal to 0. Then we can factor x, x, only 2 factors of 3, 1 and 3. The 2 is positive there, so we know we want the bigger number to be positive and smaller to be negative. So that's going to give us 1 and negative 3, or the points negative 3, 0, and 1, 0. Now we know we're on the right track if those points do seem symmetric to this what we've created. And you can see, yeah, that looks right, because they're each on 2, they're 2 units away from the line of symmetry there. So it takes us down like a frown, and on the other side as well. Okay, so now we have this good looking upside down parabola. Great job.